doing, right? This is really intended to see the project kind of come together. But if anyone has any thoughts or comments or concerns about it, feel free to speak up now, send me an email, or if you want to do it anonymously, send me an anonymous note through Piazza. I don't want to invade people's privacy or anything, but I think it's kind of fun to see time-lapse of things bustling along. So that's the purpose of it. But anyway, just so you know they're up there. Or please don't mess with them too badly because they're kind of pointed at the room. If they're not, then that's kind of pointless. Other comment is, did any team by any chance take a gripper for testing? You guys did?
Yep.
Good. Well, bad, but good, because we only had 7 in the lab, and I was trying to figure out where the 8th went. So I will make the request that we please keep the hardware in the lab. And it's not that I don't trust people, but it is sooner or later, if things walk around, you put papers on top, and then at the end of the quarter, it's really hard to hunt stuff back down again. So I'm just going to request that please keep the hardware in the lab. But that makes me happy because it means we actually have all the pieces that we should. And otherwise, yeah, definitely hound our Alex and Tim if you want assistance kind of with any of the mechanical stuff. Let us know how things are going. If people had a chance to start building, I've seen some folks in the lab kind of putting stuff together, but let me know if you run into issues or trouble. Obviously, I'm hoping that we're starting to kind of put the stuff together. And it doesn't all have to be ready by Friday, but obviously the sooner we start putting it together, the sooner we can start playing with it and debugging and iterating on it. And I'm fully expecting that the first time we put it together, it'll be a little floppy here, it will be not quite right there, and we'll fix those things as we kind of go along. That's the whole point of the project, is to kind of learn as you're doing. That said, I wanted to keep talking a little bit about forward kinematics, and then we're going to jump into inverse kinematics. I don't know if we'll finish that, I don't get to that today or not, but that's obviously where we're going. And the whole point of it is you walk down, or in this case, actually up is the right word to use, up the kinematic chain. And just to kind of be totally picky about it, I put these up again. Yeah, you got to define the 0 position, which is kind of the way I threw the arm right there, in the 0 position, right? And I picked it to be not singular, and I tried to make everything orthogonal so it comes out nicely. Define the joint directions, and then I want to go through and actually place the frames and just go through that exercise. And I'm being a little silly about it, but it is the place where, especially last year, I saw so many people make a silly mistake here and there, and then spend 2 weeks trying to debug why it's not going where it's supposed to go. And so, bear with me, I just want to go through it. The only other comment I want to make is be always aware that when you talk about a point, I mean, a point in space is fine, but if you want to give it coordinates, right, I'll refer to how Einstein that everything is relative. If you want to give it a coordinate, you got to specify relative to some origin, right? So if I have a point P, I can't give you a vector of da 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 until you tell me that the origin is here, right? And then you tell me that up, left, and forward kind of have those axes. So I need to define both an origin and a set of axes. Origin to give me the distance, the axis to give it, right? And so this is just me being really bad about labeling point B, given in coordinates of the world frame, is point A plus the distance from B minus A. And if I want to add them together, they have to be in the same frame, except I'm not given this in the world frame, so I have to rotate it into the world frame, right? So that's all that I want to say there. And so basically, you've got lots of little relative steps that you go through. And then the way that I've been doing it, which is not absolutely necessary, is to start at some world frame. So I think I had X, Z, and I guess that would make Y go in, right? And that's my world frame. And then basically rotate to the frame X, Y, Z. Do people still see that? Where first it's fixed, and then step 2 you rotate. And then next step is you go up here to the fixed one, X, Y, Z, and then you rotate. So let me, just for the fun of it, don't need that. Let's actually finish the table that we're at. And so I'm going to make a table of delta X's, which is really X of the next minus the previous given in the previous, and a delta R, which is R of the next given in the previous. should be 9 rows here from world to 0 minus, 0 minus to 0 plus. Man, from 0 plus to 1 minus, from 1 minus to 1 plus, from 1 plus to 2 minus, from 2 minus to 2 plus, 2 plus to 3 minus, bear with me, 3 minus to 3 plus, and then finally it should go from 3 plus out to the tip. So, if we walk through, do you guys agree that the first transition in this case is just a push in the x-axis? And I'm going to label that A. So you agree that is A00, and I'm not changing my rotation. And then the joint doesn't move, but it just does an RZ of Q0. Does that make sense? Moved in X, rotate about Z. Next step, I'm going to move up in Z, give it a distance B, which means this transition is a 0, 0B, but it doesn't have a rotation. Should I do this, right? All right. And then you guys agree that that means I now have to rotate about the x-axis, which is going to the right. Except the way I defined it is I want it to go this way. Is that what I defined? Which way did you define it last time?
Yeah, we defined it so it rotated around the negative x-axis.
So that means that it is rotating this way, so it's around the negative x-axis, minus Q1. And then just to kind of point this out, I'm going to put the next frame then up here. And I'm going to keep my same orientations, Z, Y. But that means I have to go both this direction, C, and then up in D, right? So I'm going to do a minus C, 0D without a rotation. And then that joint, maybe it's easier, I don't know how to draw the line here, but I hope I'm in line, which is also an Rx of minus Q2. Now the question is, where do you want to put frame 3? Frame 3 has to be somewhere along this axis. Could be anywhere along the axis. Two choices come to mind. Either you leave it right there, why move it? Or you put it down here at the tip. Both totally fair, right? This is all arbitrary, so I'm actually going to leave it right there. So that means I'm going to put no displacement on here and leave it perfectly where it is. So this is frame 0, this is frame 1, this is both frame 2 and 3. So do you agree that joint 2, sorry, am I off by 1? I am off by 1. Joint 3 is then Ry of minus Q3. Right? And then the tip, I am going to put out here, and usually by convention you tend to make the z-axis be the thing that goes out the gripper. Totally a convention thing. So I'm going to put it here, x, y, z this way, which means I am going to move 0 minus E 0 and rotate x about 90 degrees. And I'll call that distance E. Does that make sense? People buy that table. I just wanted to have it there for this robot so we can see it. Yes?
I think you're missing an entry on the table.
Am I missing one? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I'm confused. Okay. Let's do this carefully. That's a joint. That's a joint. That's a joint. That is the joint. There. Is that right? So the joints being kind of the moving pieces being these guys, right? the way that I said it is they don't have a displacement, they simply rotate. And then in between are the fixed steps. So this is a fixed, this is a fixed. Does that seem right? So, there are a lot of choices here. I tend to like this strategy. The way that I would call this is I would call this the, I don't know, minimalistic kind of definition. The reason I mean minimalistic is I basically tried not to rotate anything. Right? I tried to do the minimum amount of moves to get through here, simplest as I could do. Just for the fun of it, let me put next to it a different option. So I'm going to do the same delta x, delta r, and actually let me draw the lines in here so that I don't get myself confused again. But there's a lot of times if you actually want to put this in the URDF, which I'm going to do in a moment, what you actually like is you like the motor axes to be z-axes. Because the motors are defined, and usually you think of a motor shaft as being the z-axis of its frame, which I'm clearly violating here, right? I'm rotating about x, and I'm rotating about y. So just to kind of be clear, you can decide to do it differently. So I'm going to start the same world, and guess what? The first one was z. So I'm going to leave these guys, and call this r z of q0. And that means I'm also going to move up. But then, what I'm going to do, instead of having it this way, okay, is this going to get really messy? Should I erase and put it? Let me erase it and put it in here. I am going to define z-axis to be that way, because that's actually the motor axis, right? Which means I'm going to leave my y-axis where it was, and then that means my x-axis is now up, right? Which means I have rotated about the y-axis negative 90 degrees to get there. You guys go by that? So I could equally well define ry of minus 90 degrees, in which case this guy is just an rz of q1. Okay, I got to move up, which means these guys are now in different directions. So this is now going to be d0c, right? And I will keep the frame, given that my z is the same, I'll keep y, x, kind of the same. And then rz of q2.
Are you sure that like follows the right-hand rule?
No. Let me see what I did here. So I tried to do this direction, so z being right hand being that way. Is that what you mean? X, y. Oh, I totally did. I meant to rotate. No, x, y, z. Oh, I see what you mean. Yes. I totally mislabeled that. That is x, that is y. Thank you. So now, if I want to get to this guy down here, that means I need this z-axis to point down in this direction, which means I will leave my x-axis here, but that means this is x3, and that means this is y3 going left. Right? And so I've rotated about x. And so I should rotate about x plus 90 degrees. And then RZ once again becomes, the rotation becomes RZ. Yes. And then the final one is now 0, 0 along the e-axis. And to get to this rotation in the back, I will have to do a z rotation at minus 90 degrees. Is that right? That's what I wrote in there. So that, it's arbitrary how you write this table, right? And my point is just, you gotta sit down and I'm trying to do it a little bit fast, not to waste time, but just be careful about how you do it and define those things. To me, this is a nice one because it has all of these joints be the same. And so all the fixed ones now encode everything, and the joints are all about Z. So if you're writing a loop, in some ways this is a little bit easier, but at the same time it's arbitrary. You can kind of pick what you want. Has anyone ever heard the expression did not harken back? Expression is the wrong term. Those are two names. Names of guys that wrote a paper, I think in the 70s or something. They actually looked at this formally. This was kind of the beginning of a lot of this. And the point being is when you're moving from frame to frame, you're moving from motor axis to motor axis, right? The motor axis is a line in space. What's the dimensionality of a line in space? How many parameters do you need to define a line in space?
3.
I've heard 2, I've heard 3. Is anyone going to give me 4? Okay, let's think of a line. I can move the line this direction, I can move it this direction. If I move it down the shaft, is that going to make a difference? So that move kind of goes away, but you can still move it this direction and this direction. I can rotate it this direction, I can rotate it that direction. Can I spin about the line? Spinning about the line is kind of pointless too, right? So instead of 6 dimensions, it has 4. Said another way, I can give you an origin and angles, and then where the origin along the line is different. But in any case, a line has a dimensionality of 4, which really says when I go from this frame to this frame to this frame, I need 4 parameters. And they're actually called the Norton-Harbour parameters. And basically what he does in this I plus to I plus 1 minus to I plus 1 plus in kind of these 2 steps. Basically it is a move along X, and then it is a rotate on X. It is a move along Z, and it is a rotate along Z. So that is the very original is you move along X, rotate along X. You move along Z, you rotate along Z. You move along X, you rotate, right? Where the joint is a rotation about Z, and the fixed is always a rotation about X. That is the minimal set that you can define. In which case, instead of having all these parameters, there's always an X and a Z, and an X and a Z, and an X and a Z. So if you want to save memory and have the absolute minimalistic, this is option 3. Not very hard to work. In the days when computer memory was expensive, 50 years ago, this was nice, but nowadays no one actually really bothers. You just write the full transforms and you're happy with it. Does that make sense? Let me give you, how are we doing that? I'm blazing through. A 4th option. And I'm not going to write it out, just to kind of say it. What I did here is I tried to keep everything fairly simple, and so I went kind of to this intersection point. If you want to put it in a URDF, and I want to show the URDF and kind of talk about this in a second, right? You want to probably actually draw stuff. So what I ended up doing, and if you look at the one in the homework, I didn't place the frame here, I placed it at the back of the motor. And I placed this frame at the back of this motor, and I placed this frame, well I didn't do it because this is not the real one I did. But I always place the frames at the back of the motor, because then you can draw the motors really nicely. So this is basically have the joint axis be Z plus place the back of the motor. Right, where previously we placed it kind of at the intersection points. And just to be clear, if I'm doing things manually, I go for the most minimalistic thing I can. Because if I'm writing the equations by hand and doing it analytically, I don't want all these lengths and parameters in there. I want to keep it as simple as I can. If I'm going for a URDF, I might place the frames a little bit more complicated, but that way I can draw stuff more easily kind of in that definition. Which means I want to jump And let's go through that, yes. I want to jump and talk a little bit about URDFs. Because what I'm going to ask you to is basically do this by hand and then put it in a URDF and have it draw on screen and have it actually automatic, right? And so the URDF file is the universal robotic description format. Which is really an XML file. Before I actually, yeah, sorry, can I be really bad? I skipped a piece that I was going to talk about. I will definitely get to this, but before I do that, let me do one quick thing. Talk about transform. Because that's actually what ROS is built on, and so I just want to say this out loud before we get into it. So we have talked so far about an X and a rotation being kind of the forward kinematics of the joint values. These two together give you, quote, quote, your pose, your transform. So what you can define is you can define a T-matrix which has the rotation matrix in the top left, which is a 4x4. And then it has the X vector, and in the bottom it just puts 0, 0, 0, 1. You guys seen that? I get a few nods and a few not nods, so let me go through it really quickly. And this is always, I apologize, there will always be some folks that have already seen stuff and some that aren't. This is kind of the hard thing about this class. There's always good mix in it. But the reason you do that is basically, now rewrite this equation. If I write, let me erase the whole thing. If I write the transform of coordinate system B relative to the world, I'm going to write RB relative to the world, XB relative to the world, 0, 0, 0, 1. That is going to be equal to RA relative to the world, XA relative to the world, 0, 0, 0, 1, times RB relative to A times XB minus A relative to A, 0, 0, 0, 1. Which is nothing other than just doing the concatenation of the two. If you look through this matrix multiply, if you take the first three columns and multiplying here, you're taking this 0 multiplying by the X vector, so that doesn't matter. So you're getting rotation times rotation. Which means the final rotation is just this rotation matrix times this rotation matrix, which is this equation. If you take the last column multiplied out, right, you get exactly the RA times XB minus A piece, plus you get this, plus XA, which means you get exactly the XB. So if you're doing this on a computer, a lot of times, rather than carrying an X and an R and having two separate equations, people put it in a 4x4 matrix, fill the last row with zeros and ones, with 3 zeros and 1, right? And that way, you transform matrices basically just become this concatenation. So those steps become just multiply, 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 done. Does that make sense? So it's really a notational simplicity. But so then people talk about the T matrix as the transform matrix. And Ross actually calls it TF. And so you will see that notation in Ross. But that's basically what that is, which means you can just multiply them together. And so in Ross, there is a TF dot set the rotation, set the position, give me back the pieces, whatever it is, kind of is the classes. Does that make sense? So that means that now instead of X and R being my Fkin of Q, right, all I'm going to do is T is going to be Fkin of Q. That means I have now just one equation that I've imported here. So, and I erased it, I did erase it. That means that if you look at the fixed steps, they're just a fixed T matrix. And then you look at the joint ones, they're just a rotation about Z, and then you've got a fixed T matrix. And so basically you store the fixed T matrices and you multiply everything together, and that's what the function is. So you can put that in the URDF. The URDF is an XML file. Here, let me actually, has anyone looked at it? Let me show it. So we're going to ask you to actually put that table. We're going to ask you to generate the table, and then we're going to ask you to put the table in the URDF format, which is going to, hello, look like that. Is that showing up yet? Let me actually start my VirtualBox so I can run it. Yes. 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 Let's start that in the background. Lights. So this is in the example packet, right? So you've got this. This is the URDF file. And if you look at it, it is exactly that table. That's basically what it is. It starts with links. So a robot consists of a link and a joint, and a link and a joint, and a link and a joint, and a link and a joint. A joint has a parent and a child, right? And so the link world goes to motor 0 base. And then the motor 0 base goes to the motor 0 output. And so base is what I defined as the minus, the one that's not moving, and the output is the one that's moving. And so be aware, the name of this guy is totally irrelevant. It's a fixed one. It doesn't matter. Then this one is the one that is continuous. That name is the name of the heavy motor. And that's how Ross ultimately coordinates everything, right? So in your URDF file, you say which motor is going to be which joint. Hence, the joints are all named, and this name shows up in the URDF. And so you got to change that to whatever motors you're going to have in yours. And then you just kind of go through that sequence. And so the URDF file, in principle, is just a list, and it goes all the way down to tip, right? Motor 1 output, motor 2 base, motor 2 output, and you can name them however you want. And if you look carefully, you'll see that for the continuous ones, I have an axis of rotation. And the way I did it is I actually have this be the z-axis, this is my z-axis, and so I did everything on the z-axis. And then for the fixed ones, I have an origin, which is just where the new origin of the next frame is. So that's our shift, right? That's an XYZ shift and a rotation, RPJ being roll, pitch, yaw, being rotation about X, Y, and Z. Does that make sense? It's just taking that table and putting it in there. So if I run this thing, what are the chances it's just going to work? I haven't set it up. Come on, virtual machine. So notice that all I'm going to do is say Ross launch, homework 5 code, view URDF. Oops. I don't know where those came from. Because I'm too lazy to type all my Ross runs commands. And that's what you get. And let me briefly hide the model and hide the tip point. I'm going to hide those things for just a second. And I think I showed this on Monday. This is basically, oh, come on. Can I make this smaller? How do I make this smaller? Oh. Here are the sliders. And so you can see it. And so it has, you can see both the fixed frame and you can see the rotating frame, right? So if I rotate, you can see that it's rotating about that axis out to that frame. Does that make sense? And so it gives you the 3D view. The lighting is still bad, sorry. Okay. Note that it does RGB. RGB is XYZ. So R, red, green, blue is X, green is Y, Z Z is this way. And so yes, the motor is rotating about Z. That motor is rotating about Z. The last one does too. I just didn't put it there. Does that make sense?
R is X, G, R is Y.
RGB,
Yeah.
red, green, blue.
And
It's X, Y, Z.
Okay.
So that way, I can never remember, I always have to think that through. It's like red is X, green is Y, blue is Z. That's the definition that they use, which if you think that through, it's fairly straightforward. So we're gonna ask you to do just that. Does that make sense? So the only comment is, actually, here, let me write this out. I ran a launch file. Let me show you briefly. I'm not gonna spend a lot of time on this because I think you guys can figure it out quickly. This is the launch file. A launch file basically says all these ROS runs that you would normally type, they're all in there for you. You don't have to type them all out. So if I just look at it, this is a node. The node is basically the equivalent of doing a ROS run. And so what we're doing is we're putting a node, which is the joint state publisher. That node basically publishes, guess what? Joint state. Which is why I call it, quote, quote, the fake heavy node. Right? That is the node that puts up the sliders. All it does is puts up sliders, and it produces that. So I could have done a ROS run joint state publisher package, joint state publisher name. I used an argument which is use GUI, so you actually see the sliders. I don't know why it just doesn't default to that, but it doesn't. Right? And then my outputs, I'm going to rebap to heavy ROS robot feedback joint states. That way I've created my little fake heavy node. There is another node in here, which is ROS's version of Fkin, and that is called the robot state publisher. And I don't quite know why they called it because it's a little funny, which is this guy. So we're going to ask you to write your functions, your forward kinematics too. But for a moment, if I jump ahead, the robot state publisher is ROS's version of it. And it publishes to, it reads from joint states, i.e. from here, and publishes transforms. And then I have RViz. Sorry, I have to scroll down to actually see that. Which is the visualizer, which then shows you what that is. So those are the nodes running what you just did. Does that make sense? So same nodes and same everything. I could have run ROS run joint state publisher, ROS run joint robot state publisher, ROS run RViz. I was just too lazy to keep typing. I think we're at a point where we understand all of this and it's easy to put in a file and just run it, right? So take a look at it. The one piece that's also in here is your forward kinematics. So we're going to ask you to basically write the same node that ROS already implements for us, but basically read the joint states and output a position of the tip and do it ourselves. Because if I look at it, I then turn on the tip point and the tip pose. And you can see that that point and that pose kind of coincides. If I move them, you'll notice that it lags a tiny little bit, just because the way the node runs. Come on, move. Boop. Right, you can see that it jumps back a little bit. But basically, the point and the axes coincide with what they did. And so this is my very simplistic debugging, right? If the outputs don't match, you got a bug in your code. And actually, what I'd be really tempted to say, if you got a team, have one person make a table and implement the URDF. Have another person implement the table and put it in an Fkin function. Right? And then take them care, and then see if you get them to line up. And they should line up, because it should be the same thing. Right? Whichever table you use to build the URDF, you could use a different table to build the Fkin. It doesn't matter. The result should always be the same. The table is your choice, right? So you can do different for different ones if you want. Does that make sense? The URDF, to go back to it, basically just has links and joints in it. But at some point, you actually want to see what it looks like So I made a longer version of it, which has the same thing. It has link, joint, same thing. But then you go down the bottom and it has graphics. And it defines materials, which are just colors. And then it defines all kinds of objects. And so the link is now a visual box of this size at this location. That table is attached to the world coordinate frame by a fixed joint, which means I've attached basically this box to the world frame, right? The motors. The motor is, again, a visual that now takes an SNSTL file, a mesh file, and it attaches it to the base of motor 0. So that when I turn that on, I get, whoop, pop, that. Right, so here's a big box on the bottom, here are the individual motors and all the other boxes. Because if you're going to view it, it's kind of nice to actually see the robot. So I haven't explicitly asked you to put those in. You can put them in if you feel like making it look pretty. You don't have to. Sometimes it's nice to just see the frames, but obviously it's nice at some point to visualize the whole robot and see those. If you're really snazzy, you can download, I mean, you saw like the motors actually look like the real motors because I just used their CAD file. If you're going to do all of this in CAD, let's see if I can actually zoom in on that motor, right? They actually look like the right things. If you're doing it in CAD, you can actually export a mesh and load the mesh in here and then have it look like exactly what your links look like. Or what I cheated is I just made them boxes. You can make them boxes, you can make them cylinders and spheres, or you can make them full-on meshes. And that's all just for the graphics. It doesn't do anything else in that. Does that make sense? So the XML file is a robot. Inside of that robot are joints, right, which connect two links. Inside of those are links, which basically can have visuals. They can also have a collision parameter, which basically gives a very simplified bounding box if you want to check for collisions. And so I won't talk about it now, but the URDF file obviously becomes this multi-purpose thing. And so one of the things is you can define all these links and then say how big approximately are they with like just rough cylinders, and then do fast collision detection of all these things against each other so that it kind of doesn't hit itself. So we might go there. It also has inertial parameters. So if you actually want to tell it what it weighs and everything, you can tell it that too. And that's if we want to do simulations and stuff, kind of that's where those things go. You can also put in sensors, meaning, for example, cameras. So a lot of robots have a camera on the head, right? Or a sensor here or a sensor there. And so you can specify in the URDF file where that sits. And that means that RViz can project it in the right place and kind of put everything geometrically together, and the transforms can map it all around. Anyways, I feel like it's one of those things where play with it and it should be fairly straightforward. Thoughts, questions on that? So what we're going to ask you to do is basically run the joint state publisher through the robot state publisher to RViz, and then make your own node, which is an FKIN node of your own, which creates a point or a pose, which you can also visualize, so we're doing kind of double. So yes, I'm asking you to kind of do what ROS can do. But A, this is kind of the bread and butter of robotics, it's worth understanding. B, give me 2 or 3 minutes, and maybe we'll talk about it. Is that forward kinematics is fairly straightforward. What we're really going to care about is actually the inverse kinematics. And for a lot of the projects, they're not going to be 6 DOFs. So ROS has some solvers in them, but A, they don't always converge, right, because you can run into singularities and issues. B, we only have 5 DOFs, so they can't do the 6 DOF. So there's a good chance that we're going to have to start doing them ourselves. So having your own FKIN helps a lot in doing that, because you need the FKIN to check the IKIN and do iterative solvers and stuff like that. And so yes, it looks like it's duplicating stuff that you could have done with just raw things, but we will use that code, so it's not wasted. So I'm going to start fresh on Monday and talk about item. What I want to spend the last 10 minutes about is just briefly talking about analytic solutions. So all of this was obviously, I don't think I need that one anymore. Let me put that away. Lights on, turn the projector off. All of this was iterative, right? And you just run a loop, and it's all numerical. Especially if we talk about solving the inverse kinematics analytically, you could also do all of this analytically. Right? And so that is why I actually started with the minimalistic approach, because you want the fewest parameters in these equations if you're going to write them by hand. And I would actually go even further than that and do this. If you look at this robot, do you agree that A and B are kind of pointless, right? They're fixed. This point is never moving. A and B you can just add on at the very end, right? They're not really part of a complicated calculation because this is really, in some sense, a fixed point no matter what you do, and then you go from there. C. What value does C give you? If you build a robot the way the picture is, you need C to be correct. Absolutely. But if you think about what the robot is doing, right? It is doing I'm reaching out and I'm rotating around. Can you build a robot where C is equal to 0? All that you have to do is kind of push it back and forth until this point sits right above this point, right? And make C 0. So I'm actually going to suggest that as you design these and start building it, if you can somehow do it, I mean, D, this length, we need that length, right? We need the length to reach. Can't avoid it. C is totally avoidable. And yes, if I do the forward kinematics with all of this, I can put it in. It's not a big deal. But it's a lot simpler, especially on the inverse kinematics if you don't have it. So this is where I do the minimalistic kind of table, but then I also try to avoid all parameters, in which case I really want to set C equal 0 if I can. Because if you think about it, then this becomes a cylindrical coordinate system, right? Cylindrical coordinates for joints 0, 1, and 2. Right? The way that I have this, and it'll be a little different in all projects, the tip doesn't matter as I spin this guy, right? So bear with me for a moment. Or, actually I can go one above that. Let's say I make my little robot. I now define this guy, and I'm going to be good. And define my motors pushing back just a little bit. Define out my hair. If I put a gripper out here like this, I'm going to call this the wrist point, right? And this is my kind of, I don't know, this is my base point, my starting point, and call this my tip. Let me just focus for a moment on kind of this piece down the wrist. Do you agree that that is now cylindrical coordinates? Meaning, I could write things like X, Y, Z is going to be, I should just write this, so I don't go completely nuts. You agree that from the side view, right, what you have is this arrangement. So if you call that H and this R, do you agree that X is going to be something like R cosine Q0, R times sine Q0, and H? And R is going to be L1, L2, Q1, Q2, do you agree that that is L1 cosine Q1 plus L2 times cosine of Q1 plus Q2? And H is L1 sine Q1 plus L2 sine Q1 plus Q2? So if you make all the parameters really simple and go to this piece, you can actually just straight out write this down analytically. Do you guys buy that I can create an analytic inverse to this? I won't try to do it today, and we'll go through the full inverse kind of process next week. But I just want to bring to your attention that if you design it such that it has very few parameters, it means that you can actually find an analytic solution to these things and make your life a lot easier than having to do in kind of approximate iterative solvers. And the last thing I'm going to say in that context, and then I feel like I've been babbling enough, or we'll finish the inverse next week, is that means that I will many times think of the robot in cylindrical coordinates out to the wrist. Then to get from the wrist to the tip, if basically, here, let me redraw it. I have this, and then I have my gripper. If I know what my orientation is supposed to be, right, then I can immediately transfer that wrist point out to the tip point along those axes. So to get from the wrist to the tip is usually fairly straightforward. If the wrist is kind of this spherical. So a lot of times when you see robots, you will see them such that the wrist, if you actually do it, humans do it pretty well. This axis, and this axis all intersect in my wrist. Right? Which means I can decompose my arm into a wrist that does orientation and my outer joints that do positioning. And so I'm bouncing a little bit, but basically I'm flipping this and taking this and arguing when you design the robot, you can design it in theory arbitrarily, but in practice it may help to do that and split it kind of in those subsections. It's warm in here, right? You know what? I think we should stop. I've been babbling enough. I wanted to go through it kind of carefully, and I would go through it the long way because I want you to be systematic as you go through the homework. It's not supposed to be super deep, and I feel like I have killed the topic. Thoughts, questions on this? We will pick it up and basically talk about, now we have a forward solver. And potentially we can, and I'll go through it in detail, but we can do kind of an analytic version of the forward solver too, or you can just kind of numerically calculate it. And the big question will be, if I give you a desired place where you want to have the arm be, how do you do the inverse? And that will either be an analytic inverse or it'll be a numeric inverse. But the big thing that we'll have to pay attention to is singularities and branches. And I already hinted at them before, right? There's elbow up, elbow down, there's all these different configurations that you can be in. And so it's not just a, here's write the function, it is write a function and be aware of all those things so that you know what cases you're picking. But we'll do that next week. I feel like it's that kind of time to have some coffee or something.